5 red, what is the probability of picking a blue ball? Sorry for that. If there are 10 balls in a bag, 5 white and 5 red, what is the probability of picking a white ball if you send your hand in the bag? Second question, name 3 kinds of religion practiced in the world. Name 3 kinds of religion practiced in the world. Third question, is statistics necessary when dealing with probability? Is statistics necessary when dealing with probability? Okay, you can call us or text us on the number 6811638660. 6811638660. Good afternoon, Mr. Theodore.
Good afternoon, Mr. Frank, and good afternoon to all the listeners out there. You are welcome to the program.
Okay, thank you very much. Good afternoon, Mr. Dr. Tanju Koto. He is a research strategist and analyst, so we are very fortunate to have him on board today.
Good afternoon to you, Mr. Frank. Good afternoon to all the listeners. I'm happy to be here to share with you and grow with you in this discovery of probability and statistics today.
Right, thank you very much. So, Mr. Theodore, as you say, you have probability and statistics for us today. So the floor is yours.
Greetings once again to you all listeners out there, and welcome to the program. Today we are going to be discussing on statistics and probability. Statistics and probability. Probability in particular is something that we use it every day. We always calculate when we are going somewhere. You always try to get the probability of this happening. If you have to do this, this will happen. If you have to do this, that will happen. So you try to calculate. Probably sometimes when you're going out, you want to maybe to see a friend, and you calculate the probability of meeting that friend at home at a particular point in time.
Probability of getting an outcome.
Yeah. So generally, the probability of a particular outcome of a trial, that is an attempt at something. The probability of a particular outcome of a trial is expressed in calculating probability. You express it as a fraction of, let's just say, let's just use the constants a and b that we usually use in mathematics. It is expressed as a fraction a over b, where a is the number of ways a particular event can occur and b is the total number of probable outcomes of the trial.
Okay, so what you're saying is like if I have 5 fingers, someone has to touch a finger. The probability of him touching my index finger is, since my index finger I have just one of it, 1 all on 5.
Yes. Let us take a very trivial example, like a coin, a 100 francs coin. We have the head and we have the tail.
Yes.
Right?
Yeah.
So you have just 2 sides of the coin.
Just 2 sides of the coin.
So when you toss the coin, there are only 2 probabilities. Either you have a head or you have a tail.
So what's the probability now of getting a head?
So the probability now of getting a head, using what I just explained here, a over b, right? Since the total probability, you can only have a head or a tail, that is 2. So the total probability of that outcome is 2. No matter how you do it, you always have 2 outcomes.
Yes.
So now the probability of you getting a head is half. You have to divide it. The probability, the probability of you having a head and the probability of you having a tail is 1-1.
Exactly.
You understand?
Yes. 1:1. They have equal
chances. Actually, probability. The sum of all probabilities is 1. The sum of all probabilities is 1. There are 2 outcomes. The both of them, those 2 outcomes have to add up to give you 1. They are equal.
Okay.
That is for an unbiased coin.
Yes.
There are some particular coins that they make it in such a way it favors only one side. It weighs more on one side. And when you toss the coin, that side that weighs more, it always comes. Yeah. The same thing with the dice.
The dice.
Unbiased dice. When we are dealing with probability, they should be unbiased.
Okay, dice like when playing Ludo.
Yes,
you're always looking for 6,
exactly.
But the chances to get 6 is
1 over 6.
Yes.
So because since there are 6 outcomes, there are 6 possibilities. There are 6 possibilities. So for each and all of those 6 sides of a dice, 6 sides, that's the number from 1 to 6. So there are 6 possibilities. And in those 6 possibilities, all of them have to add up to give you 1. So therefore, the probability of you picking a 1 when you throw the dice is 1 over 6. You understand? The
Yes.
probability of you picking 1 is 1 over 6. The probability of you, let's say, picking a number that is less than 3, right? If the probability of picking a number that is less than 3, we have two possibilities. We have 1 and 2.
Yes.
And each of them are 1 over 6, 1 over 6. So the probability of you picking a number less than 6, you add 1 over 6 plus 1 over 6, which gives you 2 on 6. That is the same as 2 on 3. When you put them in their lowest form. So you see, probability is something which is really, really interesting.
Please, if we come back again concerning taking the possibility of getting a number lower than 3. I think you said something very striking there.
Get the probability of getting a number less than 3.
Because now it's a general statement. It's not specific on a particular number. So it's a set of numbers.
It's a set of numbers that you have to. Picking a number less than 3, there are 2 out there. There is only two numbers that are less than 3.
Yes.
From 1 to 6.
Yes.
Right. So the probability of you picking numbers that are less than 6, there are only 2 possibilities.
Either you pick 1 on 6 or you pick 2 on 6.
Either you pick 1 on 6 or you pick 2 on 6. So the probability of you getting that number, you have to add
the probability of each.
The probability of each.
Yes.
That is the 1 on 6 plus 1 on 6, because all of them are equal.
Yes.
Right? All of them, the probability of getting any number is 1 over
Exactly.
6, since there are 6
Exactly.
sides. So you get 1 on 6 plus 1 on 6, it gives you 2 on 6. The probability of getting numbers less than 4 is the same thing you are going to do. 1, 2, and 3, they are less than 4. So that is 1 over 6 plus 1 over 6 plus 1 over 6, which gives you 3 over 6.
Yeah, which is like half.
Exactly.
Okay.
You can. There are so many ways you can do it. You can say odd numbers. When you roll a dice, what is the probability of you picking an odd number? How many odd numbers are there between from 1 to 6? If you get the odd numbers, we have 1,
Yes.
3. I think 1 and 3.
Yes, for odd numbers.
1 and
yes.
3.
Yes.
You have 1 and 3. 1, 3, 5. 1, 3, and 5. 5 is an odd number. 1, 3, and 5. So the probability of you picking that you have 1, 3, and 5, you add 1 on 6 plus 1 on 6 plus 1 on 6. Having an even number,
Yes.
is the same thing. It's the same thing. So we have talked about the unbiased coin. I'm sure that is it's something that we do every day. When we want to play our football matches,
exactly.
One person will pick a head, the other person picks a tail. We toss the coin. Then the person who picks the tail first, then you get to choose, and the rest. At least we all know the drill when we are playing football. Yes, we all know the drill. So also in probability, we have I don't have a job, and I sit at home, right?
Yeah.
And you are going to work. Those are two independent events. Yeah, you going to work has nothing to do with me sitting at home. Those are 2 independent events. There are so many things we do in life that there are sometimes we even engage in arguments with our friends, right? Over some things that we don't. It is not actually connected, but out of sheer frustration, you just get unnecessarily upset and angry over. That's the probability, independent events in probability there. The fact that this your friend is doing this thing and you are not doing it, it makes you feel a type. But whereas those 2 things, the fact that you are doing your own thing, they are not connected.
So it's independent in the way that, okay, as you said, you're jobless and I'm going to work. If I stop going to work, it doesn't change your situation.
It doesn't change my
So
situation.
Those are independent. I just wanted the listeners to be clear about
those
that.
are 2 independent events. So at least I'm sure in probability, let's give we can still give an example.
Yes, please.
In probability, let me still use the coin and still use the dice. The probability of tossing the coin, the probability of you are tossing the coin and you are throwing the dice, right? Those are 2 events happening. So the probability of, maybe let's say, taking a head when you are tossing the coin, and when you throw the dice, you pick a 3. Those are 2 independent events, because
they're not related.
the fact that I pick a head doesn't necessarily mean I must pick a 3.
Yes.
Each time I throw the dice, any number can come, because the probability of them, they have equal probabilities of coming, as well as the coin has the equal probability of having a head or a tail. But they are not connected in any way. One does not affect the other. The fact that I throw the coin and I have a head does not necessarily mean it's going to have an effect of whatever number I'm going to get when I throw the dice. You understand?
Yes.
Those are two independent events.
For those who are just tuned in, you're into Science in Action. Science in Action, a program which is being carried out by Daltonum of Science under the sponsorship of Senator Lionel Fondensen. We have some questions because today we are talking about probability and statistics. So I'll read the questions again so for those who are just coming in can catch up. The question number 1. If there are 10 balls in a bag, 5 white and 5 red, what is the probability of picking a white ball if you send your hand in the bag? What is the probability of picking a white ball? Second question. Name 3 kinds of religion practiced in the world. Name any 3 kinds of religion practiced in the world. Third question. Is statistics necessary when dealing with probability? Is statistics necessary when dealing with probability? There are cash prizes to be won which you can use as airtime or convert to data for internet, since a lot of e-learning is demanded nowadays. We have kits also to help you fight against the coronavirus, like hand sanitizers, hand wash, and liquid soap. So you call or text us on the number 681163860. I repeat, 681163860. Yes, Mr. Chiodo, you were talking about independent events, which you've explained very, very clearly to us.
Yeah, yes. I'm talking about independent events, and it is interesting because it's the preliminary stages, and when the time comes to them to get to the complex ones, they really give up. That probability master is that topic over hard. I know your feet. Like I said the other time, I know many students out there, if there was a possibility of removing mathematics, they were making mathematics like an elective, where like how you choose science and arts. When you're in the ordinary levels, you choose whether you're doing science or you're doing arts. And irrespective of whether you're doing arts or you're doing science, you must do mathematics. If there was a possibility of taking off mathematics, like somebody will probably leave mathematics and take philosophy. But the fail to understand that mathematics is something that is very interesting. So part of the things that we are discussing here is trying to demystify mathematics, because a lot of students think that maths is something that is only for people who have brains. All of us have brains. If you get to look at it cleanly, all of us have brains. All of us are intelligent. Some people might be quick in picking up things, but that does not mean with time, if you are serious, you cannot meet up the pace. You can actually meet up the pace. You might be slow, but it does not mean you're dull, like they say it. So it is something that is really, really interesting, and I want to encourage each and every student out there to pick the interest in mathematics. You said it the other day, like we discussed the other day over Ocean City Radio.
Yeah.
Yes, they have to develop that interest in order for them to be able to grasp these little things that they will need when they get to meet the complex stuff. So there is also something called mutually exclusive events.
Their probability to occur comes down to 0.
So once this one happens, the other one cannot happen.
Yes.
But now when you're tossing a coin, it's different. Either you get the head or you get the tail.
Yes.
Yeah, either you get the head or you get the tail. So those are just some of the.
Okay, we have a caller coming. Oh, just missed the call. Yes, go on, sir.
Okay, those are just some of the few subtopics under probability, and we one of the things that also helps the students to be able to understand probability better, it makes things easier, is this thing they call tree diagrams.
Tree diagram.
They are drawing a tree diagram. I don't know, you have never heard of tree diagram in mathematics, probability. A tree diagram, you can answer a whole section, a good section, and obtain very, very good marks by just using tree diagrams.
And how is the tree diagram?
And it's tree diagram. It makes it looks really, 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 really easy. With the tree diagram, you get to. Let me just define what a tree diagram is. A tree diagram is used to show the probabilities of certain outcomes occurring when two or more trials take place in succession. Right? Talking about, for example, talking about a ball. Right? Let's say we have 4 balls in a bag. Right? Let me say one red ball, 2 blue balls, and that is one red ball, 2 blue balls, and 1 black ball. Let's just give it a rough example. And somebody sends their hands in the bag, right?
Yes.
Now, the probability of getting you already know that there are three
balls,
three
yes,
colors
yes,
of balls in the bag.
yes.
So, the fact that we have let me just bring it down to something very easy. There are 3 balls. Let me use 3 balls. You have 3 balls: red, blue, and black.
And black.
So the total probability of getting a ball, of getting 1 ball is 1/3.
It's 1/3.
Right.
Yes.
Now, imagine you send your hand in the bag, you pick a ball. After picking the ball, you put back the ball. When you want to pick again the second time, you put back the ball in the bag to pick for the second time. You discover that word. Now, the probability of you getting a ball still is 1/3. But now we are doing it for the second time. So doing it another second time, that tree diagram now comes. The tree diagram now comes in making you see, because sometimes in mathematics, when they just give things in English, students get very, 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 very scared, and the thing sometimes it looks very, very complex and complicated. Like all the these few explanations I'm not giving now. When you express it using the tree diagram, it makes you understand the English better. And that is one of the things that most students don't do when they're treating mathematics. Sometimes the teacher just gives you English language. When I use English language, I mean setting the equation in English, right? Just so to see if you better appreciate, if you can connect that English to the mathematics itself. That they can interpret what the English is saying. Because by drawing that tree diagram, it helps. That shows that you are interpreting what the English is saying. So if you're able, the best way for you to be able to appreciate that English language is by drawing that tree diagram.
Let me try to use another means to convey that idea of the importance of the tree diagram. In data analytics, for example, which is one of the applications of what we are discussing now, probability and statistics generally, there's what we call data visualization. Now, what that does is it puts the first order relationships of your data into view, into picture form, because some people are very visual in how they understand things. So, for example, if there were, let me say, 6 balls, instead of telling the person that, okay, there are 6 balls, you have 3 balls which are green, 3 which are blue, the visualization will put a graph or a picture that shows 2 green, 2 yellow, 2 black. And once the person sees that picture, it immediately tells the person the entire story. Which you could have been saying in using words. Yes, to explain. Yes. So that's one other way of looking at that tree diagram.
Yeah,
yes.
That's very true. That's very, very true. That's very, very true. And when when we are drawing the tree diagram, depending on let us go back to the ball, the 3 balls you have in the back. When you are doing it the first time, you have the red ball, you have the blue ball, you have the green ball. Let's just use that example. When you're sending your hand in the back for the first time, there are only 3 outcomes. Either you get the red ball, you get the blue ball, or you get the green ball. And each of them have a probability of 1/3 for you to get the color. The probability is 1/3. And when you pick the first ball, you throw it back in the bag, and you want to go back, you go the second time to pick the second ball. there is also 3 probabilities. Where you get the red ball, the blue ball, or the green ball. Still the same thing. And when you are drawing the tree diagram, the first instance when you are doing the first pick, you discover that you have the ball in the back and 3 how can I put it? 3 lines, 3 parallel lines.
Yes.
Let's just use parallel. 3 parallel lines, where each of those 3 parallel lines from the back represents each of those colors. Right?
Yes.
Now, each of them representing those colors, you have the green, the red, and the blue, and you green, the red, and the blue. You put the ball back. The second time again, each of those green, red, and blue, all of them, when you are picking, when you're picking the second time, there is still equal probability for all of them. So you come to realize that now, if they get to ask you a question, like you pick the ball for the first time, right? You put the ball back in the back, you pick it again for the second time, and they tell you what is the probability of you picking. You pick for the first time, you pick a green. You pick for the second time, what is the probability that when you're picking for the second time, you probably pick a blue ball? So when you have drawn that tree diagram, now you just go to the tree diagram and you follow the line. This first time, this was like this. This second time, this was like this. You just take the 2 of them and you add, and you are good to go.
I think from what you've said so far, what I can understand is when it comes to probability, there are 2 events: independent events and mutually exclusive events. Independent events.
Independent events. They are mutually exclusive events.
Yes. Independent events are those which occur irrespective of the other, and they can occur just
independently. They occur independently of each other.
Of each other.
They don't have any. One does not affect.
One does not affect the other. And the example you took was throwing a dice and tossing a coin at the same time. So we might be playing a game where they say, okay, if your results are 6 heads, you win. Yes, you understand. So those are independent. You have to get a 6 and you have to get a head. Yes, you see that. Yeah. Then now when it comes to mutually exclusive are when it can just be that. So let's take a simple example like a penalty shootout. Either the player scores or the goalkeeper catches.
Either the player scores or the player does not score.
Yeah, sure. Cannot say the goalkeeper catches the ball because there are some very good players who can send the ball way over the pole.
Yeah.
Yes, okay. So thank you for that clarification. So now the tree diagram, as you explained, is just a representation. Because I know like what we have permit me to go a little bit far away, like in the binomial theorem, there is a Pascal's triangle, which explains everything. Once as you carry out your Pascal's triangle, yes, it comes out very well.
So whatever you want to do, you just go to your Pascal's triangle. Whatever question they give you, you go to the triangle and you have a look.
So now we are encouraging the students that go back to your books and study the tree diagram, how to go about
how to draw the tree diagram.
Because the shortcoming of what we are doing here is we are on air. We cannot take a blackboard now and explain for you guys to see. So go back to your books and study the tree diagram. And one thing which I realized about probability is just yesterday when
analysis and then interpretation. Now, why do we bring in the notion of probability? First of all, remember, once you are talking of outcomes, the likelihoods of outcomes, you are talking about probability. Because probability basically is a consideration of the likelihoods of one or more outcomes happening instead of other outcomes which have the same chance of happening. That is why so they do not constitute a discussion, strictly speaking, of likelihood of occurrence again. Now, since in statistics we are talking about the collection or the gathering, the analysis and the interpretation of data so as to either predict an outcome, determine an outcome, or identify an outcome in terms of whether we're talking about basic descriptive statistics or predictive statistics or things like that. Because we're talking in terms of outcomes, we must be looking at the likelihood of outcome A happening instead of outcome B happening, where we have only 2 outcomes of A and B, or the likelihood of C happening when we have 3 outcomes of A, B, and C. Now, the reason why it's important for us to look at the 2 of them, statistics and probability, relating, is because very often, unfortunately, math teachers, maybe because of the context in which they find themselves, they do not teach probability as connected or as related to statistics. They teach it as a porcupine quail on its own direction. Yes.
Yeah.
But the thing is, you cannot properly do probability without statistics. Now, what we have been talking here about 3 balls and 2 balls and which are green, that is statistics.
Yeah.
And until we have such data, that statistics, we cannot talk about the likelihood of
An outcome.
an outcome in that area. But it's true that I said in the beginning when I was defining that we're talking about large data, but
Yes,
I'm using
yes.
I'm using that just to show you.
Exactly. To
Yes.
also understand.
Now, let me give a practical example of where they are using probability, but you need statistics to be able to use that probability effectively. I'm hoping that most of our listeners are football fans. Now, what is the probability of Messi playing well in his next match if the next match is against Cristiano Ronaldo?
And the next match is away.
And the next match is away.
We know that. Not the
Exactly.
Barcelona. Not the Barcelona.
Exactly. So for the coach to be able to make that determination and then know how to play Messi, he needs to collect data. What's the data that you collect? Data from previous matches
Yeah.
with similar circumstances. Remember, we
Yes.
need to be dealing with similarity of circumstances. What are the other matches that he has played against other teams where Cristiano Ronaldo was playing? What are the other matches that he has played away? How did he perform? Based on that data, we now begin to analyze the data. So as second half, for example, it means that for us to increase the likelihood